Hello everyone. In this video we will be discussing improper integrals. So thus far we're used to seeing definite integrals just in the form integral from a to b of f of x dx, right? Where a and b are finite numbers, and we know that this tells us our signed area with regards to f. So what we haven't dealt with yet are having issues like this. So consider the function 1 over x, right? So when we're looking at this, and we'll focus mostly in the first quadrant here. So what if I want to integrate from 0 to 1? So we have an issue here, right? So if I say 1 is here, then this is all this area. But we're used to this signed area being a finite number, right? And we're not used to having to deal with a function going off to infinity within these bounds. So also similarly, we could ask, what is the integral from 1 to infinity of 1 over x? And in that case, we'd be talking about this blue area underneath the curve that goes on infinitely in the right direction, while the former went up toward infinity. So these are two examples of improper integrals. Okay, and so we're going to use a somewhat familiar technique of approximating these seemingly infinite, troublesome integrals by finite ones that we know how to deal with already. All right, so let's look specifically at the example from 1 to infinity of 1 over x. So that's this shaded area here. So something that we've done in the past, right? So for instance, with Riemann sums or with slopes of tangent lines, right, we would just take off smaller bites, deal with those, and then take a limit to infinity to get the exact area or the exact slope of the tangent line. So we're going to do a similar thing here. So what do we know how to deal with, right? We don't know how to deal with this bound going off to infinity, but if I chop it off at some finite piece and just deal from 1 to b, well, this area is very easy to deal with, right? We know how to deal with that. And so the idea is, if we take this finite piece and make it bigger and bigger, right? We take b to infinity, then this should give us the actual area under this curve from 1 to infinity. So what we do is we turn this into a limit. So this is the limit as b approaches infinity of the integral of 1 to b. Right, so exactly this red area underneath. And now for this integral with finite bounds, we're fine, right? We can just do this as before. So as long as we keep our limit here out front. Okay, so what is this? This is the natural log of x, where we're evaluating from 1 to b. Well, the natural log of 1 is 0, and so this just becomes the natural log of b. And so what happens to the natural log as its argument goes to infinity? Well, it's just going to go off to infinity, right? Very slowly, but it does eventually do that. So this area under the curve is infinite. And therefore, in our language, we would say that this improper integral diverges. Okay. So now let's look at one where it converges. That is, where we actually will get a finite number, which may seem weird, but it turns out if something is going to 0 fast enough that even though it goes on forever, that it's small enough there as it goes to infinity that it's actually a finite area. So for our next example, let's look at the integral from 0 to infinity of e to the minus x dx. So, right, e to the minus x, it looks like your exponential decay. And so we are looking at the area on the right side. And as we know, right, with exponentials, this is going to decay towards 0 very quickly there. So let's see what happens. So again, we want to translate this into a limit, right? So we want to deal with these finite pieces. So we'll again take the limit as b approaches infinity, 0 to b of e to the minus x dx. This integral is pretty easy to do, right? It's just a very small substitution that you can probably just eyeball at this point. So we get negative e to the minus x from 0 to b. And then plugging that in, right, we get negative e to the negative b plus, because minus the negative, e to the 0, which is 1, right? And so then what happens as b goes to infinity? Well, the 1 doesn't change, right? This guy just hangs around. And then here we see that this exponent is going to minus infinity as b goes to infinity, right? So this is like 1 over e to something really large, which means you have a massive denominator. So this guy is going to be going to 0. And thus our limit is actually going to be 1. And so again, this may seem like a surprising result that, okay, we have area, this band is going to go on forever, although it's getting thinner and thinner as you go right. There's actually only a finite area, and in fact, a very small finite area of 1 underneath this curve. And so the fact that this is finite, we would say that this integral converges as opposed to diverges like the last one. Okay, so now let's gather just the general strategy and language here. Okay, so let's go ahead and talk about the definition of what an improper integral is and what it means for it to converge or diverge. So here, I'm just going to call this I so that I don't have to rewrite it a whole bunch, but let I be the integral from a to infinity of f of x dx. Then we define it to be this limit as b approaches infinity, as we've been doing in our two examples. We say that this integral converges, improper integral converges, if this limit is finite. And then we say it diverges if the limit does not exist, okay, or, goes to infinity. So it's not finite. So I'll add that in there to make sure we're taking care of everything. And then this is not the only way that these can appear, okay? So for instance, one can also go from negative infinity to b, right? So basically just we're flipping things over the y-axis and kind of having the other issue of if we traveled infinitely on to the left rather than to the right. And this is what you probably think it is going to be. So here our lower bound is going to be finite, and we'll take the limit as it goes farther and farther left. And so again, a very similar definition. And so after you have an exercise, I'll go ahead and talk about kind of the other end of things like we saw with 0 to 1 of 1 over x. So for your first exercise, I want you to evaluate this improper integral. So determine whether it converges or diverges first, and then if it does converge, determine the actual value. Okay, so now let's look at the other end of things, right? So thus far, we've really analyzed when our domain was infinite, right? Where we could go infinitely to the left or to the right. Here, our domain is finite, right? We're just between 0 and 1, but our range is infinite, right? 1 over x goes off to infinity as you get really, really close to 0 there from the right. So this is an issue as well, right? Because we're not just looking at some clearly finite area. We're used to having things be bounded. So how do we deal with this? Well, it may not seem clear what we should do, right? Because it seems like, okay, hey, we have finite bounds. But if you think about it, if you're going to evaluate things, right? So for instance, what is the antiderivative of 1 over x? It's going to be the natural log, right? But the natural log is not defined at 0. And so while 1 is okay, 0 is kind of an issue, right? We have an asymptote here. And so we're again going to change our lower bound and say as a approaches 0 from the right, so it won't ever be equal to 0. We don't have to worry about plugging in 0 to the natural log when we take the antiderivative, but instead we'll take things really close to 0 and then take the limit. So we'll do that from a to 1 of 1 over x dx. So then this turns into this limit, right? We get the natural log from a to 1. So we know that the natural log of 1 is 0, right? And so we have, again, our limit. So we get 0 for the natural log of 1 minus the natural log of the absolute value of a. So as a is approaching 0 from the right, this value in here is really, really small. And so for the natural log, that means it's going to minus infinity, right? But we have a minus out front. And so our area is going to go off to infinity. So again, this is an improper integral because of this asymptote here. and we end up getting infinity, and so this diverges. Okay. So for exercise 2, I'm actually just going to have you look at the same function as before. And so we'll do dx over x cubed, but now just from 0 to 1. So again, 1 over x cubed is going to have a similar issue, right? In that when x gets really, really small, 1 over x cubed gets really, really big. You again have an asymptote at 0. So I want you to go ahead and deal with this improper integral as well. Again, determine if it converges or diverges. If it does converge, go ahead and give the number. Okay? Thank you for watching.